Okay. Hello everyone. My name is Mohammad Sar Mehdi. I'm a Master's in Automation Engineering student at the University of Bologna, and this is basically my master thesis. So my master thesis is about predicting the trajectory of dynamic obstacles for advanced driver assistance systems, so ADAS. And my supervisor is Professor Luigi Stefano, and I'm a student of Masters in Automation Engineering at the University of Bologna. And so there are two reasons why I'm making a presentation about my master thesis and uploading it on YouTube. So primarily, I want to explain my research to everyone. And second of all, I'm actually doing this as a form of rehearsal before my final presentation in front of the committee at my department. So yeah. Okay, so let's move on. So first I'll define the problem that I'm trying to solve. So as I explained earlier, I am trying to predict the trajectory of other moving objects from the perspective of the car. So this could be a self-driving car, or this could be a normal car. So you could have like a self-driving car that is trying to navigate, and if it knows the trajectory of other moving objects around it, it's better able to make driving. It's able to make better driving decisions. And obviously, even if there is no self-driving car and you have something like an advanced driving assistance systems like ADAS, so in this system, the driver can be better informed about the future position of other moving objects around him or her. So these moving objects could be they are mainly other cars and people, pedestrians, and cyclists. So these are the three main classes of dynamic obstacles when we talk about predicting the trajectory of moving objects from the perspective of a self-driving car. And so egocentric perspective means the perspective of the self-driving car, or the car. Okay. Okay, so why am I doing this? Like, what's the importance of this research? So, I mentioned it earlier. I'm doing this for driver assistance system, so ADAS. So, you can have this system that informs the driver. So it tells the driver that that this car that is on its right or left. It's going to go to this position in the near future, and so that's one obvious application of this. And the other application, which is something that I will talk a little bit in the at the end of my presentation, is reinforcement learning. So we train self-driving cars using self-driving car algorithms using reinforcement learning. So in reinforcement learning, you have an agent, and that agent is in an environment, and so the way you train the and so if a self-driving car, if it knows the future location of all the other moving objects in its vicinity, it will be able to make better driving decisions based on that. So you can think of it like this: when you're driving a car, you don't just look at the current position of all the other objects in your nearby surroundings. You also try to anticipate where those objects are going to be in the near future. So you could be at an intersection, and there's a car with a certain orientation and at a certain distance from you, and so you look at the car and you think that, oh, this car is going to maybe try to go towards the right, towards the left, and so this you make your driving decisions based on this information. So if we can do the same for a reinforcement learning agent, this will allow that reinforcement learning agent to make better driving decisions. So it will be trained in a better way, and so that's like a really good application of trajectory forecasting. Okay, so before I talk about my algorithm, I will talk a little bit about the research that has been done in this field so far, and then I will talk about the shortcomings of that research. So starting with this thing that you see here. So this was done in 2017. Was done by researchers in Stanford, and as you can see, this neural network architecture is very complicated, and so this the idea was to like separate, to have a sample generation module and like a ranking module. So the sample generation module, it generates like multiple candidates for trajectories based on input data, and input data is like the input position of the object whose trajectory you are trying to predict. So you take those as input and you make multiple predictions based on that, and then you refine those multiple predictions using this ranking module, which is basically basically uses inverse optimal control to like make the predicted trajectories more sensible and like more accurate. And so as you can see here, this is like a really complicated neural network architecture, and in the original paper it took them almost a week to like fully train this architecture on the Kitty data set. And so so you can see that it takes a lot of time to train this, and I mean, so yeah, this was the approach done in 2017. It was interesting, but now I will move on and talk about another approach that was done. Oh yes, but before that, this is basically the output this is like a sample output you get for this method, desire method. And then this is the paper from 2018. So this is only done for pedestrians. So here what they did was they wanted to predict the trajectory of pedestrians for in a surveillance setting. So you had like surveillance cameras, and you had video, you had like this video stream coming from the surveillance cameras, and you had to predict the trajectory of pedestrians based on the video stream alone. And so what they did was they once again have this like complicated neural network architecture where they basically use a combination of fully connected layers and like LSTMs, and they combine the features that they extract from different pedestrians, and they combine it into this crowd interaction module because they want to combine they wanted to understand how the participants in the crowd were interacting with one another. And so they did this using this crowd interaction module, and then this crowd interaction module would ultimately give like the displacement, the future displacement for each for each crowd participant. And so yeah, this is another interesting approach from 2018. And so this is like a sample output from that paper, from that neural network architecture. And so you can see one big difference here is that they're not actually working on video stream that you get from a dash cam that is put on a self-driving car. So this is like a surveillance camera in a crowded setting, like a railway station, a supermarket, etc. And so this, and another thing you would notice is that in this situation the background would remain more or less static. So by background I mean like the floor, the walls, the buildings, and so on. That is not the case when you put a camera on a self-driving car or on a car and you're driving the car around. The background changes, and the dynamic objects in this background, they are obviously moving all the time. So yeah, that's one key difference, but this was an interesting approach nonetheless. And then here in the same year there was this other paper where they basically, what they were doing was they were not only predicting the future location of the pedestrians from an egocentric perspective, but they were also predicting the odometry, and by that I mean the speed and steering values. And so for a self-driving car, they were predicting what kind of speed and steering value you should provide to your car, and you should provide to your car based on the other dynamic, the other moving people in your immediate surroundings. And so you predict the speed and steering values, and you also predict the 2D bounding box coordinates of other pedestrians in your immediate surroundings. And so yeah, this was also an interesting approach. And so this is like a sample output from this neural net. And so here you can see that you have the most recent observation of the cyclist or the pedestrian, and you create this like heat map which expands and gets bigger and bigger as you extend the time from the most recent observation. And so so here they are basically predicting the future trajectory of the person, of the cyclist, in the form of a heat map, which is a term that they use in their paper. And in 2019, last year, they had this really interesting approach where what they did was they combined the depth map, the laser scanner data, the instant segmentation, and the semantic segmentation. They combined all of that, and they compressed all of this information using an encoder, and then they like decompressed the resulting feature tensor using a decoder network. And then what they did was they would predict the trajectory of the dynamic object like car, pedestrian, cyclist, using this occupancy map. So in this occupancy grid, they will predict where this dynamic obstacle is going to be in the future. And so this was also like a very interesting approach. And like this is a sample output from this paper. Okay, so that was basically a summary of the literature that we have so far on trajectory prediction for advanced driving assistance systems. And so there are some problems with these approaches. So one problem was that many of these approaches, I actually only like picked a handful of papers to discuss in my presentation, but in my actual master thesis document, I do a very detailed discussion of a lot of methods that were used to do trajectory prediction, and almost all of those methods, they actually work with a static background image. So they work on video that you are getting from a surveillance camera. And so in this situation, the background is barely changing, and when you have a situation like this, the problem of trajectory forecasting becomes a bit easier. But I mean, you cannot. I mean, the problem that I'm trying to solve was predicting the trajectory of other moving objects in a situation in which the background is also changing. So in the problem that I'm trying to solve involves a dynamic background image. So like the background image is also changing because the ego car on which you have the camera, that ego car is also moving all the time. So as a result of that, you have a background image that is continuously changing. And the other problem that you obviously saw here was you have some really complicated neural network architectures here. I mean, if you just look at the 2017 neural network architecture, the Desire network, I mean, that network is just extremely complicated. It has a combination of RNN encoder decoders, like variational autoencoders, and then obviously because I think they were trying to mix in as many different types of neural networks that they could. So they also decided to include an inverse optimal control, like inverse reinforcement learning, because in hopes of getting better results. And so the problem with complicated neural net architecture is like they can be very slow. And so because I wanted to emphasize on the real-time aspect of this like trajectory forecasting problem, so that's why these sort of neural network architectures, which are very complicated, they are sort of like a no-no in this situation. And then many papers, they were trying to do the prediction in 2D space. So like I showed in a paper here that they were predicting the 2D bounding box coordinates. I mean, you're not exactly solving the problem when you are restricting yourself to the 2D space. You want to be able to predict the actual 3D coordinates, and so that's a problem. And one, like the biggest, I think the most serious problem here was many of the approaches, especially those that used many of the approaches that use neural network architectures, they are supervised learning approaches basically. And so with supervised learning approaches, you have your usual problem. So you need to have a large amount of data, then you need to train your neural network architecture. That could take a long period of time, and then even after training, there's no guarantee that your neural net will perform in an optimal way if it encounters new data. So the usual the pitfalls of supervised learning approaches can be seen here. And so now, drum roll please. I will be explaining the method that I developed in my master thesis. Okay, so my method is actually very simple. So step one, what I'm going to do is I'm going to get the 3D bounding boxes first of all, because like I said, I want to be able to do prediction in the 3D space. Like the 2D space is just not applicable. I mean, if I want to provide useful information to a car, and 2D object coordinates, they are not useful information that you could provide a car to help it make better driving decisions. So I need 3D bounding boxes. Okay, so I have the 3D bounding box, and then what I can do is, because I know in which direction this 3D bounding box is facing, what I can do is I can sweep an arc in front of the 3D bounding box. So like this is like an example here that you can see here. So I sweep an arc, and this arc, for example, this could be of a radius of 0.1 meters. And then what I can do is I could sample some points that are uniformly I could sample some points uniformly apart from each other on this arc. Okay, so I have these points that I have on the arc that I just created. Now what I'm going to do is I'm going to select a point. So I select, for example, this middle point, which is blue here. And then what I can do is I can just like push the original 3D bounding box onto this blue point. So and I mean I'm able to do this quite simply because I know the dimension and the location of the 3D bounding box. So all I have to do is I have to push this 3D bounding box onto this new location. Okay, so I mean I have done this, right? So like what now, right? So one thing I could do is I could take this candidate location of the 3D bounding box. So I'm trying to verify whether this new location for the 3D bounding box, whether this new location is a good location or not for the original 3D bounding box. So I could do this by first I could project this new 3D bounding box onto the image plane. And so when I project the 3D bounding box onto the image plane, I can use the Panoptix segmentation of the image. So Panoptix segmentation is where you label every pixel. You label every pixel with a class and instance. So, for example, if you want to know whether a certain pixel belongs to the class of road or not, you can use a neural network for Panoptic segmentation on it. And so, yeah, I have the Panoptic segmentation for the image, and when I project this new 3D bounding box onto the image plane, what I can do is I can take the intersection over union between the base of the 3D bounding box and the Panoptic segmentation of the road. And then what I can do is I can check whether this new 3D bounding box is on the road or not using this simple like intersection over union approach. And if it is on the road based on a high intersection over union, then I would say that this is a valid future location for the original 3D bounding box. So what I'm saying is that in the future this 3D bounding box could be here because here you have the road, and so it makes sense for the 3D bounding box to be here. And if that is not the case, if the intersection over union is quite low, then what I do is I simply reject this 3D bounding box, this candidate location, and then I move on to the next point on the arc. So I have several points that I have on this arc, and then I simply move on to the next point, and then I check whether this point is also I check whether this point is a possible location for the 3D bounding box based on this technique of like pushing the original 3D bounding box onto this new point, and then like projecting it into the image plane, and then computing the intersection over union between the base of the 3D bounding box and the panoptic segmentation of the road. And so just to like show by picture, so here you can see, so on the top half you have the original location for this car. So you have the original location in the form of a 3D bounding box. And then here at the bottom, you have the panoptic segmentation of the road, of the sidewalk, and the sidewalk. And so we can see that these are the original location of the 3D bounding box. And so what I can do is I can pick a location, a candidate location, which is in front of this car. So for example, here I pick this location, which is directly in front of the car, and then I compute the intersection over union between the base of the this new 3D bounding box and the road and the panoptic segmentation of the road. And so you could clearly see here that this new candidate location for the 3D bounding box, it has like a very low intersection over union with the road, and so I reject this location. Then what I can do is I can look for a new location I can look for a new candidate location for this 3D bounding box. And so I rotate my original 3D bounding box, and then I once again project this 3D bounding box forward in 3D space, and then I compute the intersection over union between the base of this new 3D bounding box and the panoptic segmentation of the road. And so we can see here that the entire base of this new 3D bounding box is on the road. And so I say that, yeah, this is a possible future location for this vehicle. Okay, but I could actually make this a bit better. So when I showed you the original diagram, the original flowchart, I had like only one arc. But now what I can do is I can have multiple arcs, and then on these multiple arcs I can sample like several sample several points here, and each of these points will be evaluated as a candidate for the future location of this 3D bounding box. And so once again I verify whether each of these points can be like a valid position of the 3D bounding box based on the same technique of rotating the 3D bounding box and then pushing it onto the new point, and then projecting that new 3D bounding box location onto the image plane, and then computing the intersection over union between the base of this new 3D bounding box with the panoptic segmentation of the road. And then I do this for all of these points, and I only use those points that have a high intersection over union with the road picks, with the panoptic segmentation of the road. And so when you do that, you have something which is like this. So in my master thesis, I like to call this a potential field. So I call it a potential field because every point on this potential field represents a potential future location for the 3D bounding box, for which I'm trying to predict the future. And that's all fine and well, but I could actually make it a bit better. So what do I mean by making it a bit better? I could actually make it more dense. And so by making it more dense, I could actually have like multiple arcs that are separated by as little as 0.01 meters. So every arc is separated with a distance of 0.01 meters. And so when you do that, you move from like a coarse representation to a more like fine representation, where you have these like future candidate locations closely grouped together. And so when they're so closely grouped together, I decided to use something like a heat map and on this heat map you could see that the locations that are closer to the original 3D bounding box, they are like red or yellow, and then as you move away from the original 3D bounding box, you get colors like green and blue. And so I mean it's the reason for color coding all of this is to let the person know that like these locations, these are like the car can most definitely be here in the near future, and while the other locations which are green and blue, it's very unlikely for the car to be at that position in the near future. And so this is basically the final output of my algorithm. It's in the form of a heat map, and I mean, aside from being very informative, it also looks very appealing because of you're color coding this whole thing. And I could do one additional thing. I could predict the actual direction the car is going to move in the future. And so, as I mentioned earlier, for every vehicle, I have this like sector in front of the car, and I have this like sector, and here the color green basically represents the heat map. So apologies for not using the same color as I showed here, but basically you could think of this entire green as like a heat map. And so what I could do is I could divide this entire sector into three like portions. So like I have a portion for the left side, I have a portion for the right side, and I have a portion for the part that is right in front of the car. And then what I can do is I can check how much of the heat map is in the left portion, how much of the heat map is in the right portion, and how much of it is right in front of the car. And then based on that, I could simply calculate the probability that the car would go towards the left, towards the right, or whether it would continue straight on. And so this is an example here. So for example, here you can see that this cyclist, if you look at the sector of this cyclist, the sector of this cyclist is mostly like concentrated towards the left or towards like straight ahead, and there's not much portion of the heat map that is towards the right. And so based on that, you can see that there's like a high chance that the cyclist would go towards the left, and then there's also a relatively high chance the cyclist would continue straight on. And similarly, you could see here for this car which is arriving at this intersection, it could either go towards the left, it could go towards the right, or it could continue going straight. And so that's something you could do by using this heat map. And one final thing I decided to also implement a speed and steering recommendation system. And so how do I do that? And so what I do is that I have the ego car, and then what I can do is I can create this green arc in front of the ego car. And then what I can do is I can check how much of the heat map intersects with the green car, with this green arc. And so we can see here, for example, that this green arc intersects with the heat map of this van on the right side. And so because there's a lot of intersection on the right side, I basically make a recommendation for steering, and I tell the person driving the car that they should steer their car more towards the left side. And so I can understand that it's hard to see here on the left side, but basically what you see here is a circle and like a line that goes straight from the center of the circle towards the circumference, and it's more like tilted towards the left side. So it's basically telling the driver that they should like steer their car more towards the left side. And then based on how much of this green arc intersects with the heat map of other dynamic obstacles around it, I also make a recommendation for the speed. And so basically, if a lot of this green arc is intersecting with the heat map of other objects, the more intersections you have between this green arc and the heat maps, the slower the speed that I recommend to the person driving the car. And so this is basically sort of like a toy, I would say, like a recommendation system that I decided to code up. And and the reason why I decided to do it was I wanted to show the potential usefulness of this heat map approach. And so obviously you could have a much better approach using something like a reinforcement learning approach, where the reinforcement learning agent could decide what steering value or what speed value it should use. And so this was just something I wanted to do to show the potential usefulness of this heat map based trajectory forecasting approach. And this is the final diagram. And so basically what you have to do here is you need to have like a stereo camera. So your dash cam needs to be a stereo camera, and so you can take the right stereo image and the left stereo image. You can use a neural network to get the depth, to generate the depth. And so in my master thesis, I decided to use MATNet, so that's real-time self-adaptive stereo. So I decided to use that approach to generate the depth map, and then I could use the pseudo lidar approach to generate like a fake point cloud. And then if possible, you can also use an actual laser scanner to generate the point cloud, or you could use the pseudo lidar approach. I mean, it's up to you. And then on this point cloud, you could apply the 3D object detector to get the 3D bounding boxes, and then you could combine that with the Panoptix segmentation, and then you could combine these two using the approach that I mentioned before, using the approach that I mentioned earlier as a flowchart to generate future proposals in the form of a heat map. And so one thing you need to notice here is that my approach is actually quite modular, and so the actual algorithm for trajectory forecasting, it doesn't require any deep learning. So it's basically an unsupervised approach for generating future proposals for other moving objects. And so I'm calling it modular because it depends on the actual approach depends upon several other deep learning approaches. So it depends upon 3D object detection and Panoptix segmentation, and if you're using the pseudo lidar approach, it also depends upon the depth generation. And so the strength, the efficacy, I would say, for this approach, it depends upon these three neural networks. And so if these three neural networks are good and they are quite accurate, then the trajectory that the heat map that you would ultimately generate would also be quite accurate. But if any of these are quite they're inaccurate or weak, then you would have you wouldn't have good future proposals for all the dynamic objects around you. And so I'm calling this approach modular because, for example, let's say there's a 3D object detector that is much better than the current 3D object detector that you're using. And so what you can do is instead of retraining an entire neural network architecture, which is something all the previous approaches so far in the literature do, you can just take the current 3D object detector that you have and replace it with the new one. And similarly, if there is a new neural network, a new and better neural network that can do Panoptix segmentation, then you can replace that as well. And so this is why this approach is quite modular. You can, instead of retraining the entire thing, you can just take out one component and put in a new one, and voila, your entire thing works even better as compared to before. And to demonstrate how important it is that the underlying 3D object detector and Panoptix segmentation need to be. So here, for example, you have an inaccurate 3D object detector, and as a result of that, for example, you have inaccurate trajectories being predicted for all of the moving objects. So you can see here, for example, this car, its predicted trajectory should be restricted towards its lane, but because we have an inaccurate 3D object detector, the forecasted trajectory is coming towards the other lane, which shouldn't be possible because of this divider here. And similarly, if you have like a weak panoptic segmentation neural network, a weak panoptic segmentation neural net. So, for example, this is something I took from the Waymo Open Drive dataset. So here, the panoptic segmentation neural net that I was using wasn't working so well, and as a result of that, you can see here that the predicted trajectory is quite fragmented, and in many cases, for example, for this for this motorcycle, it's not even complete. I mean, like it's not useful at all, and so this is why you also need a really good and accurate neural network for panoptic segmentation as well. So just to summarize, it's a modular approach which highly depends upon the strength of the 3D object detector and the panoptic segmentation neural net. And finally, the most I would like to add that the sequel for my research is obviously going to be to try this approach with a reinforcement learning agent. So like I mentioned in the very beginning, that the one of the very big advantages of predicting the trajectory of other dynamic obstacles is that you can use that information to train a reinforcement learning agent, and when you do that, it could potentially make better driving decisions. So that is definitely something I would like to experiment with in the future. And so yeah, if you've been watching the video so far, I hope you found my research to be very interesting. And I mean, you could find it, the code for this entire master thesis on GitHub. And I mean, I've also published about this, about my master thesis on Medium, so you could also check that out. And well, thank you and have a nice day.